Hi, welcome to Lesson 12G, Vectors in Space. The goal of today's lesson is to apply similar principles and processes to vectors in space as on a plane. So every time I hear or think of vectors in space, I always think,
and now, pigs in space! Starring the fatuous Captain Link Hogthrob, the recalcitrant First Mate Miss Piggy, and the describable Dr. Strangepork.
Yes, that was a childhood memory of the Muppet Show from way, way back before I grew up. If I have already. Anyways, so in vectors we deal with two-dimensional space, and we've got the y here and we've got the x here. All of a sudden we decide to change things up and we go to three-dimensional space. And three-dimensional space, the axes are oriented using the right-hand rule, and I'll show you an image that I found online in class. But generally speaking, the right-hand rules, notice how the x and y are in this orientation, but then all of a sudden when we change the into three dimensions, we've got the x coming out of the page at you. Now this is supposed to be coming out of the page, straight directly up towards the camera here, with z and y, where y and x were respectively in two dimensions. So this is the orientation mathematically for the three-dimensional space using the right-hand rule. And if we were to draw a plane here encompassing two of the axes, we would have here the YZ plane that would be drawn here. I'll show you this in a second. Using the Z and X, there would be a ZX plane, and using the X and Y axes, there would be the YZ or YX plane or XY plane. And so that would look something like this. Okay, so the XY plane is horizontal here, the YZ plane is actually in the plane of the page here, and the XZ plane is basically coming straight up from the Z axis, directly up like this. So those are some of the things that we'll note in terms of three-dimensional space. When we draw points or vectors in three-dimensional space, we need to include what's called a parallelepiped. It's basically a rectangular prism, but a parallelepiped is basically a three-dimensional parallelogram where and just very roughly, if we have a parallelogram like this, and then the sides, instead of going straight up, the sides are also, I'm not doing this any justice at all, but the other sides are also slanted, kind of thing. So a parallelepiped is not necessarily a rectangular prism. However, when we do graph points or vectors in three dimensions, we have to make the movements along the parallel to the axes. So when we were to plot a point in the two-dimensional space, it would be point xy. Now in three-dimensional space, it's of course x, y, and z. And it is pronounced Z, not Z, Z. And it would basically look like this. So if we have point ABC, which is this point right up here, that's point ABC. This is the position vector OP, which is vector ABC, column vector ABC, originating at the origin, pointing to this point. So we go A units in the x direction, followed by B units in the y direction, followed by c units in the z direction. Notice that, of course, the first one is the easy one because it's right on the x-axis. The second movement is parallel to the y-axis, and then the third one is parallel to the z-axis from there. So without this box that we've drawn here, it would be hard to determine where exactly this point is. So if I were to draw some sort of, I could draw a quick set of axes here, and do something like this, and then here for the x-axis, I always put the negative part of the x-axis as dotted. Okay, so all of these are, here's the x-axis, the y-axis, and the z-axis, and if I were just to plot a point here, we don't really know where that is, per se. Okay, so it could be 5 units in the x direction, and then it could be 2 units in the y direction, and then whatever, a few units up in the z direction. Well, it couldn't be that ridiculous, but anyways, so it's hard to tell exactly where that is without actually forming the box to see where that is. Okay, so we need to form this to kind of give definition to where is it in the front, in front of the YZ plane, to the right of the XZ plane, and above the XY plane, or where exactly is that point. So that's what we're going to need to guide us with that. In this case, this vector ABC is actually called the body diagonal. So it's going from one vertex through the main body of this parallel epiped to this vertex up here. So it's going through the middle of the body. It's called a body diagonal, as opposed to a face diagonal, which could be from here, from say this point along this face to that point. Okay, so that's a distinction between those. We'll get a little chance to practice those tomorrow in class, of course, as fun as that will be. And so then there's just a few other little details about vectors in space.
Pigs in space!
One is the position vector. It can be written as XYZ, that's the column vector here. And that can also be written as x units, unit vector I, plus y units, unit vector j, plus z units, unit vector k. K, of course, corresponds to the z direction. If we have some vector v, v1, v2, and v3, for example, if we wanted to get the magnitude of that, well, the long and the short of it is it's just v1 squared plus v2 squared plus v3 squared, and the square root of that. So that's basically, we're just adding another dimension to it. So you could find you could do it in pairs. You could find the magnitude between v1 and v2. So using this, we could find the vector in this xy plane first. So in this face diagonal here, from the origin to here, find that diagonal, and once you get this, then use this vector and this vector to find the magnitude of this vector. So we could do it in pairs, or we can just do it in one step and just do the basically Pythagorean theorem in this form with 3 dimensions. And then the last little thing, if we want to get vectors between 2 points, well, again, if we have point A, which is AX, AY, and AZ, and point B, which is BX, BY, and BZ, then our vector AB, B is would be the head of the vector and A is the tail of the vector. It would just be bx minus ax, by minus ay, and bz minus az. Z. And that would be how we would find a vector between 2 points. So that is the basic long and short of vectors in space.
Pigs in space!
So please take a look at some examples in the textbook and take a little gander at these practice questions, which I'll of course give you time to do in class tomorrow. So thanks for watching Vectors in Space, and we'll see you in class.
Hey, I'm not a lumberjack or a fur trader, and I don't live in an igloo or eat blubber or own a dog sled. And I don't know Jimmy, Sally, or Susie from Canada, although I'm certain they're really, really nice. I have a prime minister, not a president. I speak English and French, not American, and I pronounce it about, not a boot. I can proudly sew my country's flag on my backpack. I believe in peacekeeping, not policing. Diversity, not assimilation. And that the beaver is a truly proud and noble animal. A toque is a hat. A Chesterfield is a coach. And it is pronounced said, not